recognized competitive programmer. He first entered the crypto space in 2015 when working on Bitcoin-based smart contracts for financial products at Hedgy. Later, he joined the team at tZero and ported their exchange technology onto Ethereum-based smart contracts. After that, he founded an arbitrage trading company, Bitsonic Capital, where he serves as CTO today. It is my great pleasure to introduce Andrew Warshaver.
Thank you. Hello, everybody. Thank you for showing up for this. I know it's the end of the day, so you might be a little bit tired, but I'll try to make it entertaining for you. So how many of you all know how to code in some language? Okay, that's good, because otherwise it would be a bit too fast and you get lost. So a bit about what we're going to cover. First, we're just going to cover a couple historical things to bring Solidity into perspective. Review the Ethereum virtual machine real quick. We're going to run through kind of the primitives, the data types, the built-ins on Solidity, basically just highlighting the differences between it and languages you're more familiar with. And then what I want to spend most of the time on is looking at a few case studies where we'll actually get into coding. If you did bring your computer, you can follow along and compile. If not, that's cool too. I will post all the code onto GitHub after this. No promises that it's correct though. Some of the case studies we're going to look at, we're just going to look at simple token. I'm sure you've heard of ERC-20. We're going to look at a call option, which is a financial derivative. We're going to look at the Gnosis ICO model, which was really interesting with their Dutch auction, and briefly maybe talk about liquid democracy if we have time. And then just real quick talk about sort of emerging tech and drawbacks. So if you have, I was going to use sli.do, but we're not logged in up here. So this sli.do doesn't apply. So getting into history a little bit, the first programming language, was machine code, punch cards, binary. That got upgraded into assembly, so you could actually read what you were doing. Now, if you're familiar with the Ethereum virtual machine, conceptually, it's like a machine, and the EVM byte code is similar to the machine code that existed back then. Of course, the EVM doesn't actually exist in physical space, but theoretically it does. After that, we got compiled code, which was great. We could write loops and stuff, real easy. So Solidity is in this era here, where what you write in Solidity gets compiled down into the EVM. Yeah, object-oriented programming, pretty similar. It's basically structs, fancy structs. And then, how many of you are into functional programming? All right, functional programming is best programming, I like to say. So there's a lot of projects coming out that gonna utilize that for correctness. So we talked about the different programming language historically. This is a bit about execution models, right? So the very most primitive computer had no context switching. It's just one thread. Then we upgraded to mainframes so that at a corporation, a university, you can each get some time on this more powerful computer. And the mainframe is actually kind of where Ethereum fits in, where you can think of EVM as the mainframe, and your transactions is how you rent time on the mainframe. Networked execution, changed everything. But also, the EVM is like a mainframe, but also with that, it's almost a regression because we've evolved past mainframes now. And it's that's a trade-off to have one computer that we all share, It's not going to be as fast or efficient as decentralized networked stuff. But yeah, maybe there's some model coming up that won't have the same sort of bottlenecks. So, how many of you are familiar with the EVM? You know what it is. Okay, so not too many of you, so I'll do this pretty thoroughly. So, the EVM doesn't know anything about Solidity. There's actually a number of different languages that compile into EVM bytecode, and Solidity is just one of them. And really, I just think of it as a giant state machine that has two lists. One is the list of accounts and how much ether is in each account. And the other is a list of smart contracts that have been deployed and the code for that contract and the data that is currently in store for that contract. Now, every Ethereum transaction then just causes a bunch of different sequences on the EVM, updating some state potentially or moving some ether around. And one last bit about the EVM is that each transaction is like an atomic unit. So if it gets interrupted, if it fails for whatever reason, if it throws an error, those changes get rolled back. That's pretty important with blockchain stuff. So now let's get into actual code that you can write. So this is a pragma, which is just a directive to the compiler. This is a good way to make sure that the environment you're compiling under matches the programmer's intentions, because Solidity is so new that sometimes the version updates will break old code. They'll change, right? They'll change the syntax, they'll change some functionality. And when they do that, the major or the minor version number changes. So like 0.5.4 is going to be a bug fix, or it's at least not going to be breaking backwards compatibility. But 0.6 will probably break something backwards compatible. So I normally use this second statement here to allow bug fixes, but anything else I want to review. So we have standard value types like you would expect: Booleans, integers, unsigned integers. They always initialize to basically all zeros. One thing that's different to like in C, you have like a byte and a word and a short and a long, depending on how big you need, how much storage you need for your numbers. Here you actually get increments of 8, so you can do 8, 16, 24, 32, 40, just random stuff. And that's because since you're renting space on this computer, you want to be really efficient. So if you can trim things down, you do. You got to be careful working with numbers. If you overflow, it'll get truncated, it'll screw up your math. More than one DApp has been ruined by such a mistake. So we also have address types. It's pretty useful. You want to send some ether to somebody, you need to know their address. It's basically just 20 bytes in storage. You can access the current contract, just say this, and also like message.sender if you want to know who initiated this transaction. So yeah, you might initialize a contract with the location of another contract, like a price feed that it's relying on, or the multi-sig holders that are members of that contract. With an address, you can do a few things. You can check the balance. You can send some ether around. You should know that sending ether in this way is somewhat unsafe, so you will learn more about that tomorrow. We have Enums, pretty straightforward. It's just a number, 0, 1, 2, 3 in that case. We have Structs, like you would hope. Now, how many of you know the difference between a value type and a reference type? Okay, how many of you know what a pointer is? Pointers in C. Okay, good. So a reference type is like a pointer. So everything we looked at so far is a value type. Structs are going to be the first reference type that we're looking at. where if you pass it around, it doesn't actually copy the whole object. If you make some change in a deeper nested function, it will be able to change the, it actually changes the object by reference, right? There's only one copy. This does come with some caveats, like if you call out to another contract, sometimes it will have to copy this stuff. If you really want to dig into it, read the docs. Arrays are another reference type for the most part. This first one actually, bytes 2, they have bytes 2 through bytes 31 are just like special types that are highly efficient and just pack binary data together. And you can access this. You can say, a sub 0, a sub 1, but it's super efficient and it uses the exact amount of space you specified. This is a and so that first one is actually a by value. The rest of these are going to be by reference types. This is a variable length array. This is one way you could do a variable length array. This will compile, but it's very inefficient just because of the way that Solidity packs things in arrays. There's some padding. Don't use this last one. And you might just want a variable length array of integers. One last note, you see this like memory tag here. When you declare something, you can say memory or storage. Storage puts it like in the permanent storage area, like a hard disk, and memory puts it in your temporary working space, like RAM. Strings are also available natively. They're basically just an array of bytes. There's not a ton you can do with them natively. You can hash them. But if you really want to do like any string stuff, you're going to want to do it either outside of your application or use a library. Mappings is one of the more interesting types, right? You've heard of hashtables probably. Your key type has to be a primitive value type. You can't use any reference types here. So something simple. Most common thing is the address. It's the most common thing that needs to be mapped. Value can be any type, including a reference type. Nested mappings, totally cool. Works kind of like a default dictionary in Python, where you can access things even if they haven't been initialized. It'll initialize it on the fly to all zeros. One important point that differs substantially from other languages, you do not have an iteration ability over this hash table because it's actually stored. It doesn't actually store keys. It stores the hash of the key. So there's just no way, given the data, to actually iterate over the members. So if you do need to iterate over the list of addresses or whatever, you need to build some stuff on top of it. And if you want, that's just a link to someone who did. So this is an example of what a mapping definition looks like if we were going to build like a public registry. Just say, you can give us an address, we'll give you a string, that's your name. We probably want like the other direction too, so you can actually look up somebody based on a name. But we have event logging, so getting data out of the chain is like not super easy. Like public attributes of contracts can be accessed very easily at the command line, but if you want to do something like every time a certain event happens, right, you could potentially try and look for transactions that called a certain contract with a certain signature, and now you're going to have to check to make sure that the transaction exited cleanly and stuff like that. So this event logging is like a way to find out that things are happening. And there's a bunch of facilities in the built-in Ethereum tools to basically just like slurp up all the events that are happening and filter out to exactly the ones you want based on the name of the event and actually other attributes that you can add as indexed. They'll be efficiently available. One of the other built-ins is signature checking. You're not going to need this very often because you're generally going to want to design your app such that the node is checking the validity of a signature. right? Whenever you issue a transaction, you're from an address and it includes a signature already. But if you need to do certain complicated things like multisig, sometimes you want to do it this way. This is just a little bit of syntax for it. Let me see how much time we got, because the clock is actually not running. Okay. So contracts are pretty much objects. Instead of like a list of properties or attributes, it's the storage stuff. It's the stuff you keep around permanently. And you have a constructor and you have functions, right? This is pretty familiar. Also, Solidity does have a bunch of inheritance features that you might be looking for. If you know what these are, great. If not, it's no big deal. We'll be using just a little bit of inheritance. So this is an example of what an actual contract looks like. You name the contract. Here, we're keeping an address in storage. It's going to be the owner of this contract. And this is actually a really common pattern in Solidity, because oftentimes you grant the creator of the contract special privileges. They can either issue more shares or right, like destroy the contract, wind things up, or maybe even update code. Like some contracts have that, where you can update the code. And so this modifier here, this modifier, it's not a function. It looks kind of like a function, but it's actually something you can attach to other functions. And what it'll do is it'll first run your normal code, which in this case is making sure that the person who sent the transaction is the owner, the person who created the contract in the first place. And this require line will throw an exception, right? So if that's not the case, the execution will halt. And then what it does is it jumps to the function that you've applied it on. So we'll use this later on to basically give issuing rights to the creator of a token contract. So there's also a number of like modifiers that are built in. You can call a function view, which will enforce that you don't change anything in state by accident. You can call function pure, and it actually can't even access the state. And it's really just for math. And that'll give some efficiency to the compiler as well. This one, functions by default are not payable, which means like in general you can't send Ether to a contract unless that contract's code specifies like, yeah, this function, you can send money to this function. And that wasn't originally the case, but too often like it happened by accident. And if your contract's not expecting to be paid, it doesn't generally have a way to pay it out. So like that just gets lost when that happens. So you do want to be careful about that in general, and this is a good way to help make sure that you're only accepting funds when you're expecting it. We have standard visibility stuff, super public, internal, private. Should look pretty familiar. But of course, right, this is a blockchain, everything is public, so like private means only so much. All right, so what do we have available in our environment? You can pull up the current time. This is like approximate, don't rely on it to be super accurate. Right, who is the sender of this function, or who's the sender of the transaction? How much Ether did you send in this transaction? Way, if you're not aware, is like the Satoshis of Ether. So all of the like Ether values are gonna be in way. And this is just a way to refer to the current contract. So We will get into code very shortly, but first it's like, what should we code? What are these smart contracts good for? So one thing is like a price feed. Maybe some Bloomberg wants to just have an easy way to publish a price and authoritatively sign the message and say, yeah, this is the price we know. That has some drawbacks in that it's a central point of failure. They get their key hacked. Right now, some attacker can like totally disrupt any contracts that are relying on it. So if you do this, you maybe use like 5 different price feeds and drop the highest and lowest, something like that. It can be really, really good for bookkeeping and accounting, actually. That's why like the first explosion of code was for ICOs, because ICOs are just bookkeeping. In some cases, it's just a cap table if it's a security. Or, I had this friend in college that was always borrowing money, and at one point, like, he was gonna like print Josh dollars. But if we put them on the blockchain, right, we actually get quite a number of advantages to that, because if he goes and asks our other friend to borrow money, well, they can look up on chain and see, oh, you issued 400 Josh dollars earlier today. What's going on, buddy? Right, and you could even trade them. There could be, back then there was a semi-liquid market in Josh dollars. If you put it on chain, right, even more liquid. You can do financial derivatives are great because they're basically just pure math. And that's actually what we're gonna focus on for the most part. I might be biased because I worked in finance for a while, but part of what got me so excited about Ethereum is how good it is for financial contracts. You can build decentralized exchanges. There's quite a few of these out. Pretty cool. Not a ton of volume yet, but see what happens with that. You can build a registry. There's a few of these out. You can do some governance stuff. Really cool stuff with governance, actually. And this one is actually, if you've heard of like non-fungible tokens, you can basically put a certificate of authenticity on chain so that it makes counterfeiting extremely difficult, virtually impossible, because you can't, right? Like there's no way to duplicate that token on chain. If it did happen, right, maybe the artist key gets stolen and you see that a bunch of new issuances are happening. Or like virtual skins for video games and stuff, yeah. So, let's see. How many of you like want to follow along with coding? Should I just, okay, cool. So if you have a favorite IDE, go ahead and open that. I'm just gonna use Remix. It's super lightweight, it's in the browser, it's very fast, it's user interface. Right, so the first thing I want to do is, I'm sure you've heard of ERC-20, right? So we're gonna imagine like we're just gonna start working on that problem. We want to have a contract that supports multiple issuances, and the issuances should only be able to happen by the owner, and we're gonna want to be able to move the token around from account to account, only if, right, it's your account that you're moving it from. So let me pull up the ID as well. So this right here, actually, let me just pull it up from scratch in case you are as well. So you're gonna wanna click on Solidity here if you haven't used it before, so it knows what environment you're in. You're gonna wanna set the compiler. I'm using the latest standard, which is 5.11. Turn on auto compiler. And then, I guess you make a new document here. Just click on that, give it a name. I already have mine over here. Okay, so first thing here is this ownership contract. You're gonna wanna go ahead and copy that down real quick. You can grab it from my GitHub if you want to. So that GitHub Drew Shaver Solidity intro. But I'll go back to it. So the first thing we want to think about writing a contract is what sort of data are we storing, right? What do we have in storage? Any thoughts? Anybody have an idea for what sort of data we need for this token contract? Yeah? Addresses, yes. What do we need to know about the addresses? Balance, yes. So, how do we keep what type do we use here? A mapping, yes, very good. All right, so scroll down a little bit. Okay, so this phrasing here is inheritance. Basically just gives you the stuff that the other class had. And then this phrasing here, this is the constructor, and we're saying, right, we're going to use the constructor of our base class. That's all that phrasing is. Oop, is everything okay here? So, functions. We want to have an issuance function, right? And we want to have a transfer function. So, how much time we got? This stuff is pretty straightforward, right? Issuance function, you just add to the balance of the address you're issuing to. Right, it has two parameters, the address and the amount, and we're giving you more tokens. And this phrasing right here is how we apply that modifier. So before this runs, it's going to do the check to make sure that the person who called this function is the owner of the contract, make sure your permission to issue more, and then it's going to actually increment the balance. Transfer function, also pretty simple. First make sure that you have enough balance to send it, and then decrement one, increment the other. So if you want to, you can actually go ahead and deploy this. Go to this little thing over here. We're using the JavaScript VM environment. This just makes it all happen in the browser, but if you want to connect to a node or something, you can. Here's our list of addresses that we can use. We'll just start with Alice. For some reason, we have no compiled contracts. Let's see what's going on. There we go. We have successfully selected the file. So we're going to deploy this token contract. And now a lot of times when you're deploying a contract, you're going to have to give it like a constructor. In this case, right, we're not giving it anything. If you really were deploying a token, you'd maybe give it a name, stuff like that. Go ahead and deploy that. Now, after you deploy it, you can see down here we have access to its functions. So here we're just going to copy the address for Alice, and we're going to Just deploy, or just issue 100 new tokens to Alice, to herself. Now we can check the balance. This is just a getter. So, right, we just issued her 100 tokens. She has 100 tokens. No big surprise. So, any questions on this code? All good. Let's go back over here for a little bit. So, right, that's pretty basic. But there's this thing called the ERC-20 Standard, which is a little bit more fully featured, which is nice. So it has these two functions, which we just wrote. It also has a total supply function, which is useful. But it also has these extra functions, transfer from and approve. This is going to allow one account to, basically, you're like writing a check to another account. You're saying, you can take 100 tokens out of my account. And then that other account has to come along and say, oh, I'd like those. Right? So Alice can call into the token contract and say, approve Bob to spend 100. And then Bob calls transfer from, and he says, I'm going to transfer from Alice to myself those 100. You might be like, that seems like a lot of extra work, right? We will get into why that is needed very shortly. There's a couple events as part of this standard, very useful. So here's a question, right? If we're going to allow this extra functionality, this transfer from and approve functionality, what storage data type do we need to add to our token contract? Another mapping? So mapping from address to address and another mapping? Yes. Sorry, I didn't hear you at first, but yes. So it's going to be right, the address, the from address to another mapping, which is the to address to the amount. So like in this case, it would have been an entry where Alice is the first key, Bob is the second key on the submap, and then 100 tokens. Now, this standard is still evolving. ERC-20 was pretty early on, and this mechanism is a little bit clunky. So the problem is, like, right, we want to be able to send these tokens around and also have something happen at the same time. And so this transfer from makes it so that like the recipient can basically force the transfer to happen and then do their thing. Now, there's a few other ways to solve this. 777 has this notion of operators, which are smart contracts that are like basically acting on behalf of the receiver. And they can basically file a hook with the token contract. They can like tell the token contract, hey, if I receive stuff, give me a shout. I might want to run a little bit of code. And this actually allows a smart contract to reject deposits of tokens, because just like you have smart contracts that don't want to receive Ether, you might not want them to receive random tokens as well. And then you can put inside that callback, you can just fail and say, no, I don't want this token. And then the ERC-20 tries to solve it by basically you provide a callback location to the transfer function. It's a little bit more complicated, but it might be a little bit cleaner. Bottom line, it is not resolved. Still a bit of an open problem, so maybe you have another solution. That would be cool. Or maybe another chain does. Let's see. So a little bit more complicated of an example to code than just a token contract is a call option. How many of you know what a call option is? Okay, good. So it's a derivative where the person who purchased the option is going to have the right to buy the underlying asset from you at a future date. So for example, right, maybe you're really bullish on Ether right now, and I'll sell you a call option, strike it at 200 per, maybe I'll sell it to you for $10. So the problem with this contract, right? If we're just buddies and you give me $10, you're trusting that I'm gonna fulfill my end of the deal, right? You're trusting A, that I have 1 Ether stored away, and B, that I'm not just gonna disappear. That's a problem. Now, the big banks, right, they can't really run from each other, but it's still a problem because what they do is they all work with the clearinghouse. The clearinghouse keeps a margin on file for the banks, and it tracks approximately how your positions are doing. And if your positions are doing poorly, you have to put up more margin. The problem with this is that in that case, like, options are not fully collateralized. The clearinghouse is trusting the banks to account for this tail risk to an extent, because you might have 30% margin up. But if you're selling call options, like, there's no amount of margin that can cover a moon, right? Because it's basically just because there's no limit to how high something can go. So you can't just cover it with margin. But what we can do is we can fully collateralize it. So if you have the underlying set aside in a lockbox, you're good. What these clearinghouses do today is they just work all in notional USD. So back in 2008, when it looked like Bear Stearns and Lehman were going to fold, right now their positions at the clearinghouse are very negative, and the firms that are supposedly still solvent, right, they're only solvent because they think that they've, right, had positive gains on the other side of those failed trades, right? But if Bear Stearns and Lehman can't pay, now the insolvency spreads. So fully collateralized options are a solution to this, and thankfully, blockchain is kind of perfect for it. So what we're going to do is Alice is going to create a contract representing that call option, and she's going to put 100 tokens into that contract. Now she's still like legally at that time would own those tokens, but she doesn't actually control them. She can't take them out. So there's no way to back out of the trade. Now, until expiration, Bob can send 1 Ether into the contract, and then the contract will automatically settle, swap the funds. It'll send the 100 tokens to Bob, it'll send the 1 Ether to Alice, and the trade will be complete. And if expiration happens, then Alice can reclaim her tokens because Bob chose not to execute. This question, it's like the 5 things: strike price, who's the buyer, expiry time. I'll show you the code in a sec. More interesting, what functions do we need? What functions does this smart contract need? Constructor, yep. Think about it for a sec, and I will pull up the constructor. Any ideas on the other functions we're going to want? That's cool. Yeah? Yes, this will be a new instantiation of this contract for every option that's sold. Absolutely. Yeah. Yeah, it can be, and there might be ways to do it where you reuse it, and that might be a good idea. Absolutely. Jerry? A fallback, like the cancel? Oh, fallback, like if you're receiving Ether? Okay. Might be a good idea. It's definitely a good idea. We will have to add that after, I suppose. So the functions that I have here are it's pretty simple actually, right? Alice creates the contract, she sends the tokens to the contract. That doesn't require anything. And then the major function is this execute function, where Bob sends the Ether into the contract and it executes the trade, right? And the only other function is if Bob chooses not to execute the trade, we need a way to unwind it. So all we're gonna do in this execute function, we're doing 4 checks here to make sure that everything is good. We wanna make sure the function has been funded by Alice, right? That's the second line here, we're checking the token balance. We wanna make sure that it's funded by Bob, which is this third line here, where we're checking the message value, making sure that's equal to the strike price. We want to make sure that Bob is the actual person initiating this, right? If we don't have that, then Charlie can come along and just execute on Bob's contract. And then we also want to make sure that we're still in time, that we haven't expired. And what we're going to do then, we're just going to basically send the money around. So we're going to send the tokens to the buyer, and this self-destruct line will actually close the contract and lets the EVM know that we don't need it anymore. It's a polite cleanup thing, and it'll return the funds still residing in that contract to the owner. One last question here. This is actually still missing something. It does its job, once the contract is created and has been funded with the tokens, right, then the trade is certainly settled and Alice can't back out. But there's still a part of this that is not trustless, right? Bob is still buying this contract from Alice. Right, so off-chain or something, or asynchronously, Bob is sending $10 to Alice and saying, hey, please, I'd like a call option, and he's trusting that Alice is going to publish this on-chain. But we can actually expand this to do so. And you just, you basically add a second state to the function where it first starts out unpurchased, and then Bob can send some Ether to it to purchase it. You set a flag, right? And now it's live. I have the code for that too, but we don't have a ton of time left, so I'm not going to show it to you. How many of you remember the Gnosis ICO? Okay, it was pretty cool. So if you're not familiar with it, I'd maybe recommend reading up about it later. They use this model called the Dutch auction, where the seller basically starts with a high price and then goes down and down and down until they find a buyer. In this case, many buyers, right? So a Dutch auction can be used for something like IPOs, right? We're going to offer 1 million shares, and then everybody puts in bids, right? One person says, right, I'll buy 100 shares at 50. Someone else, well, I'll buy 1,000 shares, but at 40. You put all those bids together, and then you find the highest price where all the sales will be where all the shares will be sold. You can do the same thing with stadium ticket sales. They do it, every month with treasury bills. So the naive way to run this contract is the way I kind of just described, where you take in all the bids and then you look at them all and you do all this computation to figure it out. But that is quite cumbersome. So the Gnosis team came up with this really clever mechanism where the sale was going to run over a duration of time, and depending on how much time had elapsed, would have a different implied valuation. So like the very instant that the sale started, it has a very high valuation, and then as time goes on, it starts to dip and dip and dip and dip. This is the graph of what the implied valuation is based on time. Now, what this allows is both the buyer and the seller, their jobs, math-wise, are very easy. You run a little formula as the buyer that takes in the token price that you're good with, and it just spits out a block number, right? Then you go and you just wait till that block number, and then you publish your transaction. Your desired price is implied by the time duration. And inside the contract, you're just waiting for, in this case, it was 1.5 million Ether, just waiting for that Ether to arrive. Once you've hit that total, you're good. You've sold all of them, and then you just do the same math to calculate how many tokens you're dispersing. The actual sale was hilarious. Like, a bunch of people just FOMO'd in on the first few blocks, and basically the valuation was like, almost the maximum. But the contract worked as designed. Briefly, just real brief, because we're at the end, I want to talk about liquid democracy. The hypothesis on liquid democracy is that the biggest problem with government today is that districts are too large, that you have 750,000 citizens represented by one congressperson that almost none of them know or have access to. So the proposed solution is you allow people to organize in self-described little mini districts, and then you allow those mini districts to coalesce up and up, kind of like the caucus system worked in the early days, where you would put 100 people together, they would elect a few to go to the next level, and so forth. It got impractical once population got too high, but with the technology like Ethereum, it's actually pretty easy. And there's already a project out there that has some code for it. That's the link at the top. And the benefits, it gives greater voice to small special interest groups that maybe they exist geographically very disparate, but online they can form a voting block. There's some drawbacks to Solidity. It's hard to get correct. There's some projects that will be working on that. And if you want to learn more about that stuff, there's some talks tomorrow by Cheyenne and Stefan. And yeah, if you need the code, it's there. Thank you for coming and your attention.